sorry for the technical issues and the delay. But anyway, so I've been working on an iPad app since last summer. It's the first app of its kind to teach basic MRI concepts, and I work with Dr. Anand. So a little bit about the background. So MRIs are used across the country. So like for example, in 2012, there were like 308 MRI machines and approximately 1.7 million MRI exams. So the problem is, doctors, they administer these exams, but they don't truly understand how an MRI works. And so to better their own understanding and to enable them to better help patients, we realized that it was important for them to realize the background of how MRI works and like the physics behind it. So we developed an app to try to help doctors better understand these concepts. So we found that traditional textbook methods can be very, I guess in a way, like there's a lot of information that you have to learn, and so on top of learning all of like the medical terminology and all the information that doctors have to know anyways, learning extra things about MRIs was obviously not something they wanted to do, so we wanted to try to simplify it for them while also conveying the information. So again, the purpose of the app was to create something where doctors can better understand the MRI basics, but like in a quick and efficient way. And so we wanted to develop something that was engaging so that they were actually interested in the application and interested in using it. And we wanted to make sure that so after going through the app, obviously it's not completely comprehensive, but that they at least develop some sort of interest in it so that if they wanted to learn more information, they could go and do so. So some features of the app, we start off by introducing an interactive mini textbook. So there's like some basic chemistry and basic physics that you need to know before diving into MRI physics. And so we start off with explaining, okay, well, what are protons, and what are magnetization vectors, and how does that all connect within the human body. So, for example, we have an animation like, oh, tap the screen to turn the MRI on and see what happens to the protons in your body. And so later on, we also, so the whole concept that we try to come across is that these protons, they kind of, you can add their vectors together to form a magnetization vector, an overall sum. And so we create simulations to demo what happens to the magnetization vectors within your body as an RF pulse is applied to the patient, and how the magnetization vectors change over the course of when the MRI is running. So I was going to demo the actual iPad app, but due to technical difficulties, that won't happen. So I'll just kind of walk you through the images I do have. So in this specific case, we have 3 different cones, and the cones represent the magnetization vectors within your body. So by magnetization vectors, I mean the sum of all the magnetization vectors of the protons in your body. And so there are different amounts of protons in each type of tissue. So for example, the CSF, which is cerebrospinal fluid, will have a different amount of protons than fat or gray matter. And so the way the protons and the magnetization vectors change in each type of tissue varies. And so what users can do is the screen essentially starts off blank with the magnetization vectors all pointing up. And then when you apply a 180-degree pulse, what happens is the magnetization vectors tip into the 180. So if you have like a z-axis, which is like parallel to the screen or like vertical, then they would like tip down. And then as soon as this, I don't know if you can see it, but as soon as this pulse ends, then the vector will start to relax back into its original straight up position. And so that's when you see this magnetization vector going back up. So as the cones are animating, you see the graph animating as well. So you can see how the changes exactly correspond to each other. And so how do we get a signal? And how do we get a picture from that? So what happens is you apply a 90-degree pulse to tip the cones into the X and Y plane, and the magnitude of the vectors in the X and Y plane corresponds to the magnitude of the signal. So once the 90-degree pulse is applied, since the cone would tip like this, it would go down to the z-axis, it would go down to like the 0 value. And then once the 90-degree pulse has finished applying, the cones will relax back into their original position, but they're going to kind of like rotate as they go along. And the speeds at which they rotate will vary based on the different tissues, which is why they relax back at different rates. So the user can play the simulation as many times as they want. They can tap on the different cones to get the actual relaxation times of each of the tissues. And then following the simulation, we have a second simulation, which is just like this, except there's an extra graph here that actually maps the signal after the 90-degree pulse has been applied. So the key feature of our app, I would say, is our kspace game. So what happens is when you get the signal back from the MRI, it doesn't exactly correspond to an image of a head, for example. What happens is the signals create a kspace image, which would look something like, I don't have an exact diagram, but it would look something like a whole bunch of dots kind of concentrate in the center, and then they kind of like scatter outwards. And depending on the actual image, the kspace, like depending on the data you get, the kspace image will vary. And so what happens is you take all the points in the kspace image, you apply it through a mathematical formula called the Fourier transform, which will give you the data for the actual image. And so we created this game where we provide users with like a blank screen for the kspace image, and they have to tap on the screen to decode the actual image. So as they tap on the screen, the actual image will start to reveal itself. And the purpose of this exercise is to realize that, so if I tap here, for example, I'm not going to decode a point over here. And that is because, so for a kspace image, what happens is if I tap on the center, it creates, it contains information about the general overview of the image, which is why if I decode a whole bunch of points here, I'm going to start to get a general overview of the image, which we can kind of tell is a circle. And when I start to tap on the outer edges of the image, those points correspond to the details of the actual image. So as you decode the points on the outside or on the periphery, that's when you start to get a better focus of the picture. So we're going to skip the demonstration today, but in terms of, oh, is it working? But it's okay. So in terms of like what we're going to do with this app, again, the point was to create this app for medical school students, and we want to test it to see if it actually is more effective than traditional textbooks. So that was what our goal is for the future. We will try to, so rather than testing it on medical students directly, we're going to try to test it on pre-med students, so people in the medical radiation program, life science students, and then we're probably going to create 2 test groups to give one group the iPad app, give one group textbook material that we're going to create, and see, and then like obviously provide them with quizzes to see which group retains the information better. And yeah, hopefully then we can answer, ultimately, hopefully this can lead to future research on whether or not using technology for learning is actually better than traditional teaching styles, like textbooks and lectures. And a huge thank you to Dr. Anand, Curtis, Tanya, Levin, and Tasneem for taking part in this project and for helping out with the testing and the developing of the app, and of course the Faculty of Engineering for funding the project. Are there any questions? Yes, Dr. Smith.
I have a 2-part question. The first one is really simple. How many taps?
How many taps?
How many times do you tap to go to the case, from the kspace to the image?
A lot. they can like drag.
It
kind
felt
of
like it was
thing.
like pixel by pixel.
Well, yeah, well, they can like drag their finger across, and then we like read their line to like map those points. So it's not like consistent tapping. And there is actually later on, I didn't get to post a screenshot of it. We also have like a tilting version to make it more fun, so they can like tilt the iPad to decode the image, and we'll have, as they tilt the iPad, a circle like moves across the screen to kind of map which points are being decoded.
Right. So the second part, the real part of my question, the kspace stuff's confusing, and I've never really understood it. But I feel, and I know other people that don't understand it, they do lots with MRI, just treating it like an image and doing image processing and contours. And so do you really need doctors to understand kspace? Like that was what you started with, that was your premise, but I guess I'm questioning whether that's really necessary.
Well, like obviously the more knowledge you have, the better you can, I guess, like perform your job, because like the more knowledge and more background you have. So I guess that is a very good question, and hopefully we can also like test, like absolutely test that in the future.
I'd love to hear that you were going to test. That was actually my original question was going to be how are you going to show the effectiveness, but you had that in your last slide. So very good, thank you.
Thank you. Yeah.
I also have, it's kind of like a two-part question. I have two questions. So is this app supposed to replace a course or a single, like a book in the course? And do you have any way of sort of verifying or certifying that the person actually attained the knowledge in the app if you're replacing a course?
Okay, so we're not replacing any course or any textbook. We just found that based on existing material, it wasn't really effective in terms of like, so there were different kinds of resources out there, and different styles of teaching. So there are courses, there are textbooks, but they didn't really, like our goal was to try to make it more interactive and more engaging.
Okay. Does it provide some kind of certification, or just like in like an environment?
No, it's just like like an educational app.
Okay.
I just want to follow up on his question. So a few fields have interactive textbooks. So in particular for programming, there are textbooks that you can buy and they have a CD at the end. You put the CD into the computer, and then each lesson, the author talks you through it. And then they pause and they say, hey, test your understanding. And they do that for language learning as well. Is there no similar thing, as Guy said, for MRIs?
No, there isn't.
Not at all? You've
Well,
done
there might be.
literature
Well, there
review?
might be. There are some online things, and they go more into detail. But we wanted to keep it, and they focus on different things. So the ones that I was looking at were specifically focused on different sequences. So when you're imaging a patient, there are different sequences of RF pulses that you could apply to get an image. So they were talking about the different sequences. I mostly focus on what actually happens to the very basic physics.
Just another quick question. Sorry.
Sure.
Your information for the app comes from a medical professional or your own research in the
My own research.
Go ahead, Curtis, go ahead.
Okay, I'm going to ask you a few questions that are designed to more elaborately answer Dr. Smith's question.
Okay.
So, do MRIs sample all of kspace to get the image?
That's a good question.
No, they do not. Why don't they? So it's tedious to sample kspace. Do you think it's tedious for a machine to sample kspace as well?
Yes.
It is. If they wanted to sample all of it, it would take an outrageously long time. You'd have to sit in an MRI all day and night. Okay? So MRIs, do they use different sampling patterns? So when you tap in the middle of kspace, what happens?
So you get the general overview of the actual image. So yeah, there was another module part to the app where we talk about the different ways you can traverse kspace. So one way is to have like a zigzag format where you start in the top left corner and you kind of go across and then down one, come back across. That way. Another one is a spiral where you start in the center and then you come out. So yeah, I didn't get to demo that, but there are different ways to traverse kspace to find different ways to get your image.
She's not on trial here.
I
I
know.
just want to remind you, she's not a master student, this is not a defense, right? But some of you are master students, some of you will defend, so do come present. Right.
So those different ways of sampling kspace. So I'll just say this: the actual MRI machines, they give you those options, okay, and the doctors get to select from those options. do weird things happen depending on which way you pick them? What kind of things happen? There's names of them.
Yes, and I forgot what that name was.
There's artifacts and,
Right.
and aliasing. So just point out, if you know the way you're sampling kspace, you might know, like, if I get an image, oh, there's something wrong with this, I should choose a different way.
And you have one last question.
Yeah.
Actually, it's not question, it's a kind of opinion and suggestion that because all of we are computer science or related to computer science, so it would have been better if you could give a architecture of your whole modules and how they are relevant, at least one page, the architecture, then we will understand that the development effort or the complexity of the software.
Okay, sounds good.
Okay.
I'll keep that in mind for the future. Thanks.
All right, thank you again.